Welcome back. So now we are going to work on section 3.7. Notice section 3.6 is not in our syllabus. All right. So I'm using our Dropbox. Section 3.7 is optimization problems. Okay. Now, so these are what we call word problems in calculus. In solving such practical problems, the greatest challenge is often to convert the word problem into a mathematical optimization problem by setting up the function that is to be maximized or minimized. Let's recall the problem solving principles. So any word problem you have certain basic principles. What are they? First, understand the problem. The first step is to read the problem carefully until it is clearly understood. Ask yourself, what is the unknown? What are the given quantities? What are the given conditions? Second, draw diagram. There is no harm in drawing diagrams, even when the question does not ask for it. Draw diagrams for your own sake. In most problems, it is useful to draw a diagram and identify the given and required quantities on the diagram. Third item, introduce notation. Assign a symbol to the quantity that is to be maximized or minimized. Let's call it Q for now. Quantity. We like to say X, Y, whatever. Any variable. Let's call it Q. Okay. Also select symbols A, B, C, or X, Y, so on for other unknown quantities and label the diagram with these symbols. It may help to use initials as suggestive symbols. For example, capital A for area, H for height, T for time. So choose your variables thoughtfully. All right. Now express your quantity Q in terms of some other symbols using these symbols. If Q has been expressed as a function of more than one variable, use the given information to find relationships among those variables. Okay. See, the point is whatever quantity you wish to maximize or minimize, make sure it is defined in one variable. If there are more variables, look for some relationships among them. Okay. And now the last step is find the absolute maximum or minimum value of your function f being the function that determines q. All right. If the domain of f is a closed interval, then the closed interval method can be used. Either way, we have learnt enough calculus to be able to find absolute maximum or minimum of a function if they exist. All right. Let's look at an example. Okay, examples always help. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Okay, so let's see what this means. So you have some fence, you have a river, you want to fence some rectangular region along the river. How do you fence in such a fashion that you get the largest area? So here are three pictures. So there's your river, and you have used your 2,400 feet of fence material. 100 here, 100 here, 2200 here. Now that gives you a certain area. Well, here is another option, 700 on the sides and 1,000. That gives you some other area. 1,000 here, 400 there. That gives you yet another area. So the question is, how do you make sure you get the maximum area given the same 2,400 feet of fencing? Okay. Now, So we see that when we try shallow, wide fields or deep, narrow fields, we get relatively small areas. It's possible that there is some intermediate configuration. So this gives you a small area, this gives you a small area. So, well, this is just our intuition. This gives us a large area. Okay. So we want to find x and y such that the area is maximum. If that is x, that is x, that is y. Look, there is no y needed here because there's a river and a is here. All right. So x plus y plus x is the entire fence. In other words, 2x plus y is 2400. That's the very first step. 2x plus y is 2400. What is area? X times y. Now you want to maximize area, all right? But I have two variables here. I know to maximize or minimize a function in one variable here, all right? We want to express a, area, as a function of just one variable. So you want to get rid of y, eliminate y by expressing it in terms of x. So this is where we use the given information. Total length of the fence is 2400. 2x plus y is 2400. So what is y? 2400 minus 2x. That is y. Okay? So use that y in the formula for a, xy, y is 2400 minus 2x. And now notice your a is only in terms of x. All right. So what is a? 2400x minus 2x squared. Now we want to maximize a. Okay. So what is this? 0 to 1200. Well, remember, we can have, what was the question? We have 2400 feet of fencing and x are the sides. So even if all of this is 0, right? If y were 0, I still have 2x. So 2400 means this will be 1200 each. That's the maximum a can go, x can go. Okay, that's all we are saying. X, the maximum it can go is 1200 and the minimum it can go is 0. Distance cannot be less than 0. So x is between 0 and 1200. Okay. How do we find maximum? You're looking at maybe critical numbers. This is a polynomial, so its derivative will exist. Take the derivative. This gives me 2400. This gives me 4x. So 2400 minus 4x. To find critical number, take the derivative, set it to 0. Well, solve for x. You should get x equals 600. Solve this for x. Okay. So the maximum value of a will occur either at the critical number or at the end points. Okay. So find the end points. When x is 0, a is 0. X is 1200, a is 0. So this is the maximum. Okay. So that's the maximum area. And when x is 600. Another way of noticing it, find the second derivative of a. Okay. Second derivative will be negative 4. You understand what negative 4 means? Second derivative is negative, means you are concave down. Therefore, concave down means you get a maximum at that critical number. Okay. So, oops. So, x equals 600 is going to give you the absolute maximum. Corresponding y, you are plugging in 600 for the area. Corresponding y, Y is 2400 minus 2 times 600, that is 1200. Okay, if you have forgotten, go back. So this is the formula we are using. When x is 600, plug in for x, 24 minus 2 times 600. 2400 minus 1200 gives me y to be 1200. Okay, so that gives you the dimensions of your rectangle. X equals 600, y equals 1200, and the maximum area is 720,000 square feet. Okay, so let's remind ourselves. First derivative test for absolute extreme values. Find critical number. If the derivative is greater than 0 to the left of C and derivative is less than 0 to the right of C, then FC is the absolute maximum. Let's draw a picture. Okay, so say this is your number line. Somewhere here is C. Okay, if to the left of C, f prime is positive, what does that mean? Your function is increasing. To the right of C, f prime is negative. What does that mean? Your function is decreasing. So increasing and then decreasing. So that gives me C to give me a maximum. Okay. On the flip side, suppose I do the same story, right? To the left of C, my f prime is less than 0. To the right of C, my f prime is greater than 0. Then what's happening? To the left of C, I'm decreasing, and to the right of C, I'm increasing. So this gives me a minimum. All right. So this is first derivative test. All right. So this is the first derivatives test. Looking at the picture, here is another option. If f double prime is negative, that is, it's concave down. All right, that's the second derivative test. And here f double prime is greater than 0. So this is using the second derivative test. All right, so anyhow, use the first derivative test for absolute extreme values or use the second derivative test, whichever comes in handy. Okay, until the next video then. Bye for now.